Thank you very much, Tony. I'll just turn it over to you.
Okay, thanks, Wayne. Now, can everybody see that for a start? All good? Excellent. Right, I'll just keep that down there. All right. Sorry. The two satellites we're talking about here, one's called CUAVA-2, one's called Waratah Seed-1. They're the latest incarnation of a whole series of picosats, mostly various forms of CubeSats that have been launched, been designed, built, and launched by CUAVA Group, EVA's group. Feel a little bit of an imposter telling you all about this because most of the work associated with this has been done by Shuliang and Patrick, who work with EVA. They've done an amazing job. These are both 6-unit CubeSats and are designed to carry as many experiments as possible. They're passive satellites, although CUAVA-2 does have aboard it a test example of an electric thruster, a charge exchange thruster. Now, we've heard about that in the past, in the last few months. Joe Cashan, who is the person who did the work on that payload, gave us a very good talk on it, actually, and I've got a little bit of information about that, but that's really the only part of the payloads, the only thing about any of the payloads that I'm going to talk about in detail, because the payloads really are the work of the people who are running them. From time to time in the future, it might be a good idea for us to get some of those people in. I was talking to Eva today, and I was mentioning that I'd really like to see the thermal control payload, because that's something I used to do for a living. I used to be a thermal engineer, spacecraft thermal engineer, and they've got a phase change thermal control system in one of the spacecraft, and I would really love to see a bit more about that. So that might be someone we could get in to talk. Okay, so they're both technology demonstration missions, particularly CUAVA-2. The CUAVA-2 mission objectives are to demonstrate a couple of different experimental technologies, particularly the hyperspectral imager, which is a University of Sydney and experiment. It's a system to look at the ground and look at the spectral composition of the ground and make determinations about the environment, agriculture, forestry, marine environments, and so on and so forth. So it's a kind of geographic experiment, that one. There's also another thing called a GPS receiver, which is similar to what we've had before on other of the CUAVA satellites. It looks at the GPS signals from satellites in the GPS constellation, but specifically it looks at the grazing incidence reflection off oceans, and with a view to establishing the sea state. That means how big the waves are, basically. And that's done just simply by watching the spot of the point of reflection, which would normally, with a perfectly smooth sea, would just be a nice, neat little spot. But watch to see how it moves around, in effect. Scintillates, I think, is the best way to say it. And so that's that one. And there's also quite a few secondary payloads. There's a star tracker, also a USID project. The EDDI, also USID. The charge exchange thruster, which is led by Richard Bowden-Reed, but really I think Joe Cashan is the driving force before he retired for that one. We've heard about that. Perovskite solar cells, also Sydney University, led by Anita Ho-Bailey. The Magnetorker, that's something I really would have loved to have seen work. That's just basically a permanent magnet that allows the spacecraft to maneuver on the spot around its center of mass by interacting with the terrestrial magnetic field and producing torques in various directions. So it's a way of attitude control and it's electric, so it's more or less indefinite. As long as you've got electric power from the spacecraft, from the solar panels, you can do attitude control. You're not dependent on a fuel or a working fluid. And then a radiation counter. Now, that radiation counter has been a resounding success. I saw some data for it today in Eva's office, but I've got some data that I'm going to present from that today. And use that data to make a point about the vulnerabilities of very small satellites, but I'll go on into that a little bit later. Okay, there's the basic layout of the spacecraft viewed from with one of the solar panels off it. There's not a lot to say about that. The black writing is largely the housekeeping, the pointing out what they call the bus equipment, the equipment that actually runs the spacecraft. The ADCS is the attitude determination control system. The reaction wheels are also part of that. The radio is there. Battery, of course. The EPS is the electrical power system. There's also an S-band antenna, and that's been vitally important because these payloads can produce more data than the UHF, VHF radio can downlink in the time that it has over the ground stations. Now, I think the fastest data speed from the UHF, VHF is of order 9,600 baud. That's 960 characters per second. So a fair bit. You can get a fair bit of information out. There's a very large beacon, which contains a lot of information. And it contains, you could also get information about the housekeeping of the spacecraft and the, what can I say, the details about things like what temperatures and voltages and currents and the charge state of the batteries and the housekeeping stuff. They call it the Tracking Telemetry and Command Link, TTNC for short. There's also a SatLab S-band radio, which is very high baud rate, and perhaps Evie, you could correct me on this, but I think it's about a gigabit. But if I'm wrong, feel free to break in and tell me that. That's a very fast downlink, and some of the experiments that produce very high quantities of data, like the hyperspectral imager, and I guess also the radiation counter, really do need that kind of downlink rate to be able to get all the data down at the time that they're over the ground station. There's a ground station inland a bit. I think one of the Amazon ground stations that does that work for them. There's also the GPS patch antenna. A patch antenna is an antenna that sort of sits on the side wall of the spacecraft. I'll show you a picture of that in a moment. And the UHF, VHF antenna, which are basically what are called dipoles, center-fed dipoles. There's a magnetorquer, which is basically a spiral. That's the thing that interacts with the terrestrial magnetic field. A sensor to find where the Earth is. The nadir is the direction directly down. It's in the opposite direction to the zenith. There's the GPS reflectometry, which I was spoken about before. The S-band antenna is also a patch antenna. Because the S-band is much higher frequency than the UHF and VHF, you can actually get away with a physically smaller antenna, which is a really very useful thing for these very small satellites. The payload computer, which is a very good system. I wish there was actually slightly bigger, but anyhow, the magnetorquer and the charge exchange thruster, that's Joe Kashan's project. And then the star tracker, which is used for navigation and pointing accuracy, and the star tracker. So that's basically the layout for that. And viewed from outside, you see there on the lower left, I'll just see if I can point to this. Yeah, this is the reflectometry antenna, the GPS receiver. That's the hyperspectral imaging lens, so that would be pointed at the ground. This antenna would have to be pointed roughly at the point in the ocean where the signal was being reflected from. There's a small electron density antenna there that deploys that. This image here shows it stowed. And then the rest are solar panels. The patch antennas are here. As you can see, they're very small. They only occupy one unit, the side wall of one unit. The Earth sensor is very small. The magnetorquer is a very small little object there that pops out and travels around to there. It's a very simple little piece of equipment, but it has the potential to increase the functionality of these kinds of spacecraft dramatically. And the star tracker, which is down the bottom there. The GPS patch antenna is down the bottom. You can't see it there. And the that's the VHF antenna, that's the other half of the VHF antenna there, and that's the UHF antenna, and the other half of the UHF antenna, and they're fed in the middle, once you can't see it in that image. Okay, so that's CUAVA. That's the charge exchange thruster, a picture of it that I took for Joe inside a vacuum chamber, and it's actually functioning. That glow you can see coming out of the side of the charge exchange thruster is the rocket plume. It's a really remarkable little piece of equipment. It is incredibly efficient. It has a very high specific impulse. And it was a great pleasure to see one operate it. I took this photograph myself, and I have to tell you that I had to push the camera as hard as I could to get that image, because it was the situation was very dark. But we got that image. Took about 30 seconds to accumulate. It's a terrific little piece of equipment. It only uses 1/4 of one unit, and there are 6 units, so it only occupies a very small amount of the volume of the spacecraft and uses very little resource except for energy when it's operating, of course. Now, exactly the same size is the Waratah Seed-1. It's a rideshare mission, which is something that's fantastically important for universities and schools and educational institutions that would love to put a piece of equipment or an experiment in space, but can't afford to go through the torture, if I could call it that EVA has to go through to get launch permits and design spacecraft and purchase equipment and get people, I was going to say, sort of wrangle all of the various people that are needed to get to work together to get a mission like this in space. And for some quantity of money, it's not a small amount of money, but by the standard, well, compared to what it would be with a full-size satellite, believe me, it's a bargain. The users have to pay to have an experiment on the spacecraft, so that just means that institutions that can raise the money will be able to have some hardware in space, so that's a huge advantage. There are several sets of payloads. The commercial client payload is the thermal control system that I was telling you about earlier on. I've heard a little bit of a talk about that, and that's something I would love to hear more about. It's a joint mission between UTS, Mawson Rovers, and a group called Spiral Blue and SmartSat. The project is called Matilda. Curious name for a thermal control system, but I'd love to know more about that one. The University of New South Wales and USyd have got the GPS reflectometry system. That's 1 unit. Also, you notice that just next to each experiment, I've got a statement here about how big it is. 1 unit is 1/6 of the volume of the spacecraft. It's a 6-unit spacecraft. The GPS reflectometry system is also 1U. CUAVA and USyd generally, as well as the New South Wales government, have looked at this electron debris and plasma detection. It's only 1/4 of a unit. And DENEB, I don't know, and CUAVA and SmartSat, that's not DMartSat, that's SmartSat, I typed that incorrectly. The electropermanent magnet magnetorquer, which is the one I was explaining earlier on with the spiral antenna that sticks out the top of the spacecraft. And then there's a payload competition system where people, they were oversubscribed, so they had the winners of this were the materials and mechanical. I'm not sure too much about that. That's something we could perhaps get a talk about later on. Extraterrestrial power, silicon solar cells, basically. Perovskite solar cells, these are showing great promise, and there are several of those on the spacecraft. And once again, materials and mechanical. That's exposing materials to space, I guess, that kind of thing. And a computer. Now, computing in space is obviously necessary. These things are essentially computers with stuff bolted onto them. But it's not as simple as you would think, because the environment in space is exactly the worst kind of environment that you could possibly have for running a computer. And the 2 main things are the large variations in temperature, occasional variations also in power supply, but mostly temperature, and above all, radiation. And I'll talk about that in a few minutes. This is the layout, the internal layout of Waratah Seed-1. As you can see, there's essentially the same arrangement. You've got a whole series of housekeeping, bus payloads. They're not payloads, bus equipment here, the interface, the communications, reaction wheels, ADCS, and the electrical power systems, and the TT&C antenna. And then on this side, what we've got is the various payloads. I won't go into those now, as I said before, but I would really love to know more about this one. Solar cells and reflectometry. This is the outside view of it. You get a better view of the TT&C antennas here. The antennas are fed from a printed circuit board inside this panel here. The longer arms are two arms of the VHF, the shorter arms of the UHF. And we've got a GPS patch antenna on the side, the perovskite cells here. I don't know much about those. I'd love to know more. And then there's also S-band patch antennas and so on the other face. So exactly the same as you saw on the other diagram. Now, I won't go into this any more than to say what the operational success is. You can see there that there's a whole series of things that happened. And when the guys launched this thing, they were incredibly busy. Part of the problem was that in the past, when we've launched satellites and when other people have launched satellites, we get radar scans of that satellite more or less immediately. The advantage of this is that we can then get the orbital elements. We can then track that satellite more or less immediately. But these two satellites did not get scanned for nearly 2 weeks after they were launched. That's pretty unusual. And as a result, it took a while to actually acquire the spacecraft because until they've been scanned, you don't know exactly where they are. Talk about that in a minute. The commissioning for CUAVA-2 took about a week or so, and the various payloads immediately follow that. There were some difficulties with that. They got some information from the Starcross. The HSI unfortunately failed. Payload computer started to show abnormal activities. I said a little while ago that computing in space is not as simple as you would think. And as a result of that, they were unable to control the S-band, the high bandwidth antenna, and so they can't get data out of that. After several reboots, they've concluded that the payload computer is dead. There's two computers on board this spacecraft. One is the housekeeping computer, and one is the payload computer. In an ideal world, it would be nice to make them interchangeable, but they weren't. So when the payload computer failed, there was no fallback then. But they did get a bit of data out of the radiation counter, and that is absolutely fabulous data, let me tell you, and I'll show you a little bit about that in a minute. And they're also testing the data over power bus, so a kind of internal network using the power cables to communicate between the various parts of the spacecraft. Waratah Seed-1 has been much more successful, largely because they didn't have that computer failure. They've completed all the experiments on the thermal payload and the GPS payload. 7 of the 9 payloads have been successfully demonstrated in space, which is a tremendous effort, and really it's just a fantastic effort from the guys. They really do deserve a lot of congratulations for that. And they've had over 180 days in space. In fact, they've had considerably more than that now. This slide is a little bit out of date. The operating secondary payload is periodically running, and the other payloads can use the low bandwidth link. That's the TT&C link. Now, I said before computing was difficult. It's not just computing, but we have a bit of a problem with radiation in these spacecraft. They are physically small objects. You should know that the environment in space is very radiation dense. In fact, it's so dense in places that even at high-flying aircraft, intercontinental aircraft flying over the poles, you get an appreciable dose of radiation. Air crews have to limit the amount of time they spend on flights over the poles. That's because much of that radiation is conducted inwards by the magnetic fields, they're terrestrial magnetic fields. There are three tactics we can use to protect ourselves against radiation. The first thing is time. You limit the amount of time that you have to be in the vicinity of the source of the radiation. That's a problem with a spacecraft because you can't limit the amount of time. You have got to be in space, and in space is where the radiation is, and that's just nothing you can do about that. So the next thing we can look at is the distance from the radiation. You get as far from the source of radiation as you can. That's absolutely useless from the point of view of a spacecraft because you can't get away from the radiation. You are stuck with it. You are in the vicinity of radiation, and that's all there is to it. The spacecraft has got to be there. And finally, there's a thing called intervening material. That means you get as much stuff between you and the source of the radiation as possible, and specifically high Z material. That means that material with large nuclei. Now, these are small satellites of order 100 millimeters on a side, maybe as large as 300 millimeters on one side. So there's very little intervening material between the spacecraft, between the radiation on the outside and the very sensitive equipment, particularly the computers on the inside. And a lot of CubeSats, a lot of them have suffered what are called single event upsets. That's a failure of some sort due to the problems with radiation, which I'll talk about more in a moment. Oops, sorry. Now, this amazing map I got such a shock when I saw this. Patrick Opel showed me this, and I had to put it up. I wasn't going to talk about the payloads at all, but I had to put this up. This is a map of radiation counter measurements from the CUAVA-2 spacecraft at various points around its orbits. And there's an absolute shed load of them. It's color-coded. The brighter the colors, the redder the colors, the more radiation they experience. Now, if you look at these regions here, this area here is in the South Atlantic, and that's the southern part of South America, Chile particularly. You can see that there's rather more than unusually large number of red dots there, and there's also quite a few colored dots in the vicinity of the equator and at one or two other points around the globe. These regions are regions where the spacecraft has to fly through from time to time. Remember, these are polar orbits. We'll talk about that in a moment. So they have to go through every point over the Earth. It covers the entire Earth. And the amount of radiation it experiences at times is really quite extreme. And I'll give you an example of what I mean by that. When the space station flies through these regions, the crew have to retire to the lifeboats. When they know they're going to fly through this region here, they actually have to all drop whatever, well, not drop because you can't drop anything in space, but they have to stop what they're doing and go to their Dragon capsule or to the Soyuz capsule, whatever it is, lock themselves in it as if they're ready to come home, with a view to actually coming home in case the spacecraft, the station, is so badly damaged that it can't function. Then they go through the region, it only takes a few minutes, and then they get out and they have to run around and restart all the computers on board the space station. Now, the space station, as you know, is a very large object. There's a considerable amount of material between the outside and the inside, but it still damages computers. It causes quite a few computers to shut down. They've got a crew up there to reboot them, but there's no crew aboard these picosats, and it causes a lot of problems, and so it did with CUAVA-2. Over here on the right-hand side, you'll see what we call a heat map of that intensity, and you can see how much radiation appears in low Earth orbit in this region. Now, this is called the South Atlantic anomaly. So, CubeSats are always going to be vulnerable to this region of space, and actually to the poles as well. And these two spacecraft go over and under the poles all the time. So it's going to be a limitation, and it's one of the more fertile areas of research is to make them radiation hard. I'm not sure how they're going to do that. Okay, a word or two about the orbits. Just checking the time. The Orbits are sun-synchronous orbits. Now, what that means is this. If you look at those drawings, what we've got, the green orbit is the sun-synchronous orbit. That's going over and under the poles, or very nearly over and under the poles. And it has to do that for the altitude that it's working at. And as a result of that, it precesses, I'll just tap on this. It's a nearly polar orbit. It's called sun-synchronous because it's the plane of the orbit. That's the plane of the orbit there. Remains in the same position with respect to the sun all the way through the year. And I'll just get this out of the way. And the same position here. It tracks once each year, it tracks all the way around. And so the spacecraft is always seeing the sun in the same position. It's always getting the same amount of radiation. And the Earth is happily rotating underneath it, and it covers the entire Earth. For an Earth resources satellite, it's exactly what you want. It passes over every point on the Earth at the same local mean time. And that's about 10:30 or 11 o'clock in the morning, and about the same time at night. Right. Okay, that's that. The orbit is arranged so that the plane of the orbit precesses over one complete year. So that's what we mean by that. Now, orbital parameters. Orbital parameters are information that are supplied by the US government Space Force to anybody who has a registered spacecraft in orbit. They're known as Keplerian elements, or two-line elements, and they're called two-line elements because they come in two lines, exactly like that. There's a lot of weird-looking numbers there. We don't need to go into all of them, but I will show you two numbers that are of particular importance to us. The first of them is the timestamp. That's this number here. The first of those two digits there tell us are the last two digits of the year, so obviously that's 2025. The next digits are the day number of the year, and then the decimal place is the fraction of that. That is an absolutely absurd number of significant figures. And what I mean by that is that particular timestamp there implies the 25th of January this year at 05:03:31.27 seconds. Now, there's no hope in hell that they could know it that accurately, but that's the data that they give us, and that's the data we live with. Okay, the other point to note is this number here, which is known as the mean motion, and that's simply the number of orbits per day. 15.23745632 orbits per day. Again, an absurd number of significant figures. And that implies an orbital period of a little over 94.5 minutes, which is fully consistent with the altitude of the spacecraft. That information is then used to calculate what's called the semi-major axis. And I'll show you what that means now. For that reason, we apply to Kepler's laws of planetary motion. And the first of these is that every orbit is an ellipse, with the primary, that's the thing being orbited, Earth in this case, and in particular the center of mass of Earth, at one of the two focuses or foci. That's all there is to it. Take particular note of this distance here from the center to the edge of the longest axis. That's known as the semi-major axis. This distance here is called the semi-minor axis. That's incorrect. And you see it's considerably shorter than the major axis, and that's because the orbit is an ellipse. When the two are equal, it's a circle. A circle is a special case of an ellipse. The second law. The second law is interesting, and it's actually the law of motion that allowed Newton to accurately calculate the law of gravity. And I'll just see if I can get this going. If you draw a line between the center of the orbit and the center of the object doing the orbit, you have what's called the radius vector. the area that sweeps out in any equal length of time, no matter where the spacecraft is in the orbit, will always be equal. So that area there is equal to that area there, okay? And that's a useful thing to know, and it's what allowed Isaac Newton to realize that the law of gravity was an inverse square law. So that's important, but not useful for us. The third law, though, is tremendously important to us because that's what we use. The ratio of the square of an object's orbital period, the time it takes, we get the orbital period from the Keplerian elements, with the cube of the semi-major axis of its orbit is the same for all objects orbiting the same primary. And what that means is this. Sorry about the equation. A is that distance there, the semi-major axis that I pointed out earlier on. T is the time it takes to go around the orbit, the square, the period of the orbit, which I also pointed out. And that's equal just to the universal constant of gravitation, which is G, times the mass of the Earth plus the mass of the spacecraft divided by a constant. That can be approximated just as gm on 4 pi squared because the mass of the spacecraft is insignificant in comparison to the mass of Earth, obviously. Rearrange that equation to make A the subject, and we have now worked out the semi-major axis. And that is the equation that the software solves, that we use to calculate the semi-major axis for each orbit for which we have a set of Keplerian elements. And we get about anything from 1 to 3 a day, although there are these days gaps of a couple of days from time to time where we don't get Keplerian elements. And I have a feeling that that's just because there are just so many objects in orbit now that they just can't keep up. So now, we like then to look at the orbital plasma data to compare that with changes in the orbit over time. I'll show you that in a minute. This is a map of the solar activity expressed in what's called the F10.7 flux. That's the 10.7 centimeter solar flux, which is a useful proxy for measuring the activity of the sun. We are at the moment on the way down from a very, or recently speaking, a fairly big solar maximum. That means the sun is very active. It's putting out a lot of radiation. There's a lot of UV, there's a lot of X radiation, and there's a lot of sunspots, which is where some of this radiation comes from. The spacecraft was launched more or less here, right just on the downside of the peak in 2025. So it really did, in 2024. So it really was, it's copping an absolute beating from radiation. So it's no surprise that one of the spacecraft did suffer radiation damage, and it's a big surprise that the other one didn't. But it's a great effort anyway. Now, geomagnetic measurements. In order to tell us what's going on the sun, we look at particular quantities. And one of them is the 10.7 centimeter radiation from the sun, which I mentioned before. That's just a general proxy for solar activity. As you can see, there's also another number which we measure called the planetary K index, which we won't go into the details there now. Another thing called the disturbance storm time index, which tells us something about the extent to which the Earth's magnetic field is disrupted by the impingement of this material from the sun, from the solar wind. The K index tells us whether we're in a geomagnetic storm or not, whether there's a lot of activity going on with the Earth's magnetic field. And then the MG2, which is a sort of a proxy for extreme ultraviolet light from the sun. It's a ratio of 2 emission lines. And lastly, but not least, the X-rays from the sun. That's less useful most of the time because the background X radiation from the sun is fairly low, but it really peaks heavily if there's a solar flare. So that tells us how active the sun is, and in particular, if there's a burst of activity from the sun. Now, some of these quantities, are concerned with particulate matter from the sun, the solar wind. That's the KP and the DST. And the MG2 and the XRS, the X-ray, is radiation from the sun. The particulate interaction parameters are the K-index. This quantifies disturbances in the horizontal component of the terrestrial magnetic field caused by the impingement of these particles, and it's simply expressed as an integer from 0 to 9. The planetary K-index is an average, a weighted average of all 13 observatories all around the world that measure this quantity, and they're all at approximately mid-latitudes because it's really the equatorial region that matters the most for this. Any value below 5 represents relative calm, and if it's 5 or over, it implies that there's a geomagnetic storm happening. If it gets to the 8 or 9 level, you might conceivably be seeing aurora, even at Sydney latitudes. So that would be a really big activity. The disturbance storm time index, DST, is a measure of the fluctuations in the terrestrial magnetic field, and this results in changes in the equatorial ring current. So the charged particles hit the equator and are either deflected right or left and form a current around the Earth, around the equator, and this affects the strength of the magnetic field in the vicinity of the equator. A negative value implies that the terrestrial magnetic field has been weakened. Now the radiation parameters. The MG2 index, which is just extreme ultraviolet radiation directly off the sun, and the X-ray is just that. It's a measure of the X radiation from the sun. Solar X radiation is emitted during solar flares, and it is thus what we say bursty in nature. That just means that there's lots of it for short intervals and then not too much in the background. Okay. Now, towards the actual data, what you're seeing here is a series of graphs of the the semi-major axis. This is it here. It ranges from about 514. This data was accurate as of Friday, down to about 492 kilometers. The second one is the change in this quantity with respect to time. I'm going to talk more about that in a moment. That becomes important. Some of the Keplerian elements that I did not mention before are also measured here, and this one in particular is called the B star, the starred ballistic drag coefficient. They actually calculate what they think is the drag for you. It tells us, as you can see here, when there's a sudden drop, the more negative this value becomes, the more the spacecraft drops. As you can see that there's points throughout this orbit where there are significant negative values for the ADT value, the change in semi-major axis with respect to time. And these correlate pretty strongly with peaks in the drag. And that's exactly what you would expect. The eccentricity is kind of interesting. This is a measure of the ellipseness, how elliptical the orbits are. And you can see it's very wavy. And then lastly is the inclination. Now the inclination is the angle between, I'm sorry I don't have a diagram for this, between the plane of the orbit and the equatorial plane. And as you can see, that's getting dropping down here, getting closer and closer to 97.4. It doesn't change very much, but it changes very cyclically. Okay, these are then those Keplerian elements. Semi-major axis is A, the one at the top. The first derivative of that, the drag coefficient, as I said, the eccentricity and the inclination. So I forgot I'd done that. Okay, in addition to that, we look at the plasma quantities. The KP index is here. As you can see, it fluctuates quite a lot. This figure is multiplied by 10. What you see here is 20. That really should be 2, 4, and 6. So we have come close to geomagnetic storms at times, which correlate perfectly with changes in the very, very big changes in the orbit. And so that's an interesting quantity to see there. The DST becomes more negative as there is more disturbance in the Earth's magnetic field. As you can see, this particular event is about 100 days into the spacecraft's flight. There was a big event there, and then these correlate very strongly with the other events, both on KP and to some extent also with the change in altitude. And that's the F10.7 flux again that I said before, the 10 centimeter flux. Okay. And last but not least, the other quantities here are the radiation quantities, the MG2, that's extreme ultraviolet, and the X-ray flux. We came up against a bit of a problem with this, which I only just discovered the other day while I was putting this talk together. And that's that the spacecraft that we're using we're using the data from that collects this data is called GOES. Just forgot what that is. It's a little acronym. The spacecraft that we've been using is being decommissioned and is being replaced by a new one. So the data has tended to stop just a bit after 450 days on this diagram. There is now more data for the MG2 data. MG2, that's the extreme ultraviolet data, but I haven't been able to graph it yet because I've got to interrogate that data from a new spacecraft, and that only begins at around about 400 days. So that's something I've got to fix in due course, and I will do that, promise Eva. The check's in the mail. So there's not a lot we can say about that. We can clearly correlate the activity of the spacecraft with some of the activity in some of these quantities, particularly this one here. That's a big solar flare, and you can see that that correlates approximately with a sudden drop in the spacecraft altitude with that one there. Okay, DADT, MG2 index, and X-ray flux. Now, I'm going to concentrate a little bit more closely here because on Friday, Eva and I were both going through this data, and it was fairly obvious, and I'd seen it too, that at times the change in altitude of the spacecraft is positive or appears to be positive for brief intervals. Now, the spacecraft is passive. What I mean by that is that it has no thrusters aboard. There is the charge exchange thrust, but unfortunately they haven't been able to operate that. So the spacecraft should never rise in altitude. It should only ever descend. And as you can see, if it rises, that value will become positive. And for brief intervals from time to time, it is positive. That's slightly disturbing. And as a result of that, we need to do a bit more analysis of that. And I've done that here by isolating. I'll just show you what I mean. If you look at this region here, you can see that there's a region of positivity here for the CUAVA-2 spacecraft. And that seems to coincide approximately with some wrinkles in the line there. If we look at that a bit more closely, what we see is, in fact, that there are some very, very significant fluctuations in the apparent height of the spacecraft. This is the semi-major axis, but it's a good proxy for the altitude. It's showing that for intervals of time, the spacecraft is climbing. Now, that cannot happen. And that means that the data that we're getting about this spacecraft, and probably all spacecraft, is a little bit unreliable. And the reason for that is partly as a result of changes in the ellipseness, the eccentricity of the orbit, but it could also be changes in the attitude of the spacecraft. So the guys have been able to change the attitude of Waratah Seed-1, align it with in direction of travel, but they haven't been able to change the attitude of CUAVA-2 because the payload equipment, the payload computer is not functional. As a result, there will be differences in the altitude and in the DADT value particularly. And it's probable also that there are several other things that are affecting this result. The first of them is that it's very difficult to measure anything about an object that's 500 kilometers away from you at least, moving at 7.5 kilometers per second, and you only have a few seconds to radar scan it each time it comes past. So a very accurate measurement is unlikely. And also the math that they do, what they call the propagator math, so I won't go into that here because it would take ages, is it's a bit of a black box to us. We're not absolutely sure how that works. So we are seeing some anomalous readings from this, which we just can't believe. But we know that they are there, and they're all in very brief intervals. I'll just go back briefly to look at this region here, particularly this region here. You see the CUAVA-2 spacecraft has a significant period of time there where the DADT is greater than 0. And you can see quite clearly from that graph that it appears to be climbing, which it can't do. And that is that region, the last 35 days that I've been able to analyze. And as you can see there, it does appear to have a sustained period of climb after around about 520 days or so. And the DADT value reflects that. And it also comes down again here where you see this thing decay. And that I can't really explain a deviation, an anomalous deviation in the data that's that long. So that's something we're going to have to bang our heads against a bit at some point. This information here, I believe, because it reflected by both spacecraft simultaneously, you can see that there's a sudden drop in the altitude, quite a large one. There's obviously something that's happened there. We'll be able to correlate that with some of the plasma data later on. The Waratah seed data is a little bit anomalous here. It appears to be climbing for a significant period of time. And it pokes its head up above 0, the DADT, which can't happen, but individual anomalous readings are explainable, but this one in particular here, where it sustains above 0 for a considerable length of time, nearly 8 days, I cannot explain that at all, but that's the data that we appear to be getting at the moment, and that's where we are right now. What I'll do now is go through the questions, and if I don't like them, I'll let them through to the keeper, what I like to do. Now, I'll go back here. The electropermanent magnet talker, and is on both CUAVA-2 and Waratah seed and is working very well on the latter, so that's helpful for me. S-band is about 1 megabit per second, not 1 gigabit. Sorry, Eva, yes, you're quite right. I only slipped 3 decimal places. It's a very interesting photo of the thruster. I agree with you. It was a really challenging photograph to take, but in the end, it was very interesting. Polar orbits could be more dangerous to satellites. Potentially, Wayne, you're correct about that. The reason for that is you're going over and under the poles because there's a lot more radiation at the poles, and because it certainly does bring you through the South Atlantic anomaly fairly frequently. Equatorial orbits or semi-equatorial orbits also do that, but the polar orbits are much more likely to do that. The 2 orbits are slightly different. That's not so much a condition of radiation, Wayne. It's probably more to do with the different attitudes in the spacecraft. They will separate over time. They will experience slightly different.
I think I remember asking this question earlier about the 2 satellites.
They will separate over time. They were deployed into space almost at identical spots.
Yeah.
But they will separate naturally over time because the variations in the density of the upper atmosphere is at times localized, and it's usually localized in what's known as a subsolar region, and the region immediately at local noon. And as the spacecraft passes through that, it might catch a period of time where there is increased density, but the other one won't because it passes at a slightly different, at different times, and the altitude changes, and so the conditions change for both spacecraft over time. But the most important thing, I think, is that they haven't been able to orient CUAVA-2, but they have been able to orient Waratah Seed-1, and so the actual drag profile will be different.
That's why it looks like one satellite's being controlled and the other one
Yeah,
isn't.
exactly. It's actually, I think Waratah Seed-1's probably getting ahead of the of CUAVA-2.
In a sense, that's useful information though,
It is incredibly useful.
because you can now see the effect of one that's a controlled satellite and one that's not controlled, and what type of
Well,
difference.
not only that, but you can also see the relative effect of the drag.
Yeah. I mean, in some ways, even the other thing about the
Can you raise your hand?
equatorial side, I'd never really thought of that as being a big problem, but it only goes to show that the polar satellites really have to have more radiation.
They do, they do.
Yeah.
Plus also that different frontal.
Would you hit play chime?
Mm.
The different frontal area is significant, and it's particularly shows
Right.
the space station
Oh,
because
I didn't think we were muted.
Yeah, so it's actually quite interesting info you're getting back, in other words.
yeah, quite a lot of it. Yes.
Yeah, that's right.
Yes.
Sorry, Tony and Wayne, can I just slightly correct you there?
Yes, go ahead. Yes.
Actually, CUAVA-2's ADCS is working fine, and so are all of the spacecraft subsystems except the payload computer. So it actually is controlled.
Oh, okay, I didn't
It
know.
actually orbits with its with the same face as Waratah Seed forward. So that's one of the 2-unit faces.
Right. So that means that we're just seeing slight variations.
Well, that was what I was curious
Correct.
about, whether that was what was actually the difference, but that's fair enough. I mean, it's interesting you got the secondary payload working, Eva, as well now. At least you're getting something out of
Oh,
CUAVA.
they're getting quite a lot of information, particularly that radiation counter.
Yeah, that's interesting. You're getting that data out of it. Was at least it's, although you've got a problem with the payload computer, you're getting something out of it, which is good.
That's fantastic data. Really.
It is interesting. I have a student called Rayan Al-Kadri who's been working on the radiation counter data. And so we hope to start, putting some of it onto LinkedIn and so on, because it really is quite pretty. And you really see the Southern Atlantic anomaly coming out.
By me.
Tony probably wanted to say the numbers, but didn't quite have time. But the Southern Atlantic anomaly has radiation counts which are of order 100 times bigger than the values over the poles that we've yet observed routinely. So it really is huge. And yet I was, before we launched and started seeing these data, I must admit I rather poo-pooed the Southern Atlantic anomaly. I thought it would be, small potatoes compared with the poles and the auroral zone. But it's actually not. It's actually very substantial.
I'm looking forward to seeing that data change as the spacecraft orbit decays and it goes into the lower regions, especially gets below 400 kilometers. I'd love to see what those values come out as.
That will be interesting. And also comparing the radiation map with the so-called heat map or magnetic field map that you showed. Yes. That will be very interesting.
Yeah.
How different is the CUAVA-2 orbit and Waratah Seed-1 compared to the CUAVA-1?
Very. Sorry, carry on, Tony.
Right.
They're very similar, Wayne, but they're just drifting apart.
No, I'm talking about the first CUAVA satellite. How different is that?
That was at the 51-degree inclination.
Right, so that was more of an equatorial, in other words.
Closer to equatorial, yeah.
Okay, so really that's part of the reason for doing this different too, is you want to get different data. Okay.
Especially for the radiation stuff.
Yeah, that's right. It looks like that. I'd never realized that anomaly was out there. I suppose it's over South America. It doesn't affect us so much here.
Well, it affects the space station, let me tell you. They have
okay.
It's a big deal for the space station.
Yeah. You might recall there was a jet airliner that went down, must now be 5 or maybe even 10 years ago, going from Brazil to France. And apparently part of the reason for that is believed to be communication difficulties associated with radiation upsets as it went through the Southern Atlantic anomaly.
Particularly after solar flares and things like that.
Yeah, that's one of the things I hope to see is evidence of the Southern Atlantic anomaly significantly changing in intensity as the number of energetic particles drifting around the Earth in the radiation belts, some of which come from solar particles, changes. So it will be very interesting to see that.
Yeah. I'm really looking forward to seeing the changes in altitude, though. That really
Yes.
interests me. Yeah.
So you think you've got another 6 months worth of data left in it, or is it just
Oh, more than that. More than that. I think
okay?
I'll probably have another year, I would say.
Right, okay, because I know that the orbits obviously are one problem is that they're probably going to decay, although the stuff that's 500 kilometers is it's a
Yeah,
long way
it's at
up.
about 490 kilometers at the
Yeah, that'll
moment.
take a long time for it to.
Yeah, we expect it'll take something like a year to get down to, probably a year and a half, maybe even 2, to get down to 400 kilometers, which is where CUAVA-1 was. And CUAVA-1 had a lifetime of order 1 year in orbit, a little bit more. So from the point of view of the orbital lifetime, we're probably looking at perhaps 2.5 years, maybe a little bit longer. But the spacecraft components might well not last that long.
Yeah, well, that's going to be the interesting one. But then again, you're going to find out how long they last. Then that's one thing. So that'll help the people that have got the experiments up there, I'm assuming.
Yes, I have a question for you, Tony, and that just is, I think in some of the images or the data for dA by dt and A as a function of t,
Yes.
you showed some quite rapid sudden jumps in the semi-major axis, especially quite close to launch. I think it was within 100 days.
Yeah, sorry.
Remind us how big that number was. Was it about, was it 100 meters? Was it a kilometer?
Okay, so there is a big one just there from this point to that point. That's
No, I think look at one of the earlier ones, Tony.
right.
Maybe this is one of the ones that we were looking at yesterday that's correlated with. So go back to one of the ones which is correlated with dA by dt or something.
Well, that's the whole dAdt and the A over the entire.
Right. So round about day 280 or 90.
Yeah.
So at about 510 kilometers, it's quite well, I thought it was quite a sudden jump.
Yeah, there's that one there, which is this one here in closer detail. This one here was the one that had me worried. That one there.
No, but I'm interested in just in association with the space weather event. There was a change in A that was quite dramatic in time, and I think it was a change of about a little bit less than 1 kilometer.
Yes.
Change in less than or equal to a day. Yeah. So it's that one there at about day 280 or 290.
It's this one here, yes.
Yeah.
That's right.
And if you look up in the blue,
yeah,
it's quite a sudden change.
Yes, it is. There's a distinct discontinuity there, actually for both spacecraft too. There is actually a change in CUAVA-2 and Waratah Seed-1, but they're both exactly at the same moment. And the blue line completely obliterates the red line. There is a red line underneath there that you can't see. I'll have to draw.
Right. And that's, of course, an argument that this is an actual space weather event.
Yeah, that's that big event. It comes up with the 10.7 flux. It's that one. Hang on. We're at 10.7. DST. It's that one there.
Yeah.
Yeah, that's the one there. You can see it really clearly.
When was that event? Earlier this year?
It was about 100 days into the mission.
Oh, okay. So early 100 days.
No, hang on. Yeah, about 90 or 100 days into the mission. Yeah.
Around about the beginning of this year, then.
No, it was
October.
Late last year. Okay.
It was about October sometime. October.
Oh, right. Okay.
I think actually it's rather close in time to when CUAVA-2's payload computer got damaged.
Well, that makes sense because that would be the thing that zapped it.
That's what one would, in one sense, one would hope, yes.
I think so. Yep.
It's died for science.
Yes.
Oh, well, that's what I mean.
I can't see it with the
science
radiation data. I was hoping to be able to see it with the X-ray data, but I can't see anything there.
Yes, but remember, with the energetic particles in Earth's magnetosphere, there's two sources. One is energetic particles coming from the sun, which might well be correlated with the X-rays.
Yes.
But you also have the ones that are produced in the magnetotail. due to magnetic reconnection there.
Okay, so
And
that's actually, is there one of the quantities that measure that one? Because I'm not sure about.
it's more DST.
Okay, all right. So just look up a bit. DST, yeah.
Which
So
is,
that
for instance, that big event there.
very clearly there, and then similar events there, and less so later on. Yes. So there's an awful lot of information in this that's going to take a lot of analysis when I get a chance to do it. Sorry, I haven't done it so far. I've been doing this.
You've got a question on the solar radiation and its effect on the orbital decay, I see, from Jeremy.
From
Jeremy,
can't see.
in the question there. I may have missed it, but how much does solar radiation contribute to the orbital decay on these satellites?
Well, the radiation is a lot. I mean, that's if especially the X radiation and the extreme UV, because when that gets down into the sort of 250 kilometer altitudes, it heats the atmosphere up a lot, and then a wave passes up through to these kind of flight altitudes, and within a couple of minutes, it has an effect in the subsolar region.
So the lower the orbit, the bigger the problem's going to be, obviously.
No,
really? Okay.
I guess the lower the orbit, the orbit in the 300 to 500 kilometer, maybe under 500. Yeah, 300 to 500 kilometers is an area that seems to be affected. Yeah.
Yeah, jet synchronous won't be. It's too far out.
Oh no, it's way outside that. Yes.
Yeah,
Right.
so they're not a problem.
But
no. Yeah.
Tony, might you want to answer that very slightly differently, in the sense that CUAVA-1, when we did the analyses of the orbit,
yes,
what we found was that orbital changes were very well correlated with changes in MG2.
yes,
and to a lesser extent, the F10.7 centimeter radio flux. Whereas, which implies that it's the solar radiation which is sort of heating up the atmosphere a bit more, causing increased drag, for instance.
Yes, I agree. Yeah.
But I think for CUAVA-2 at the moment anyway, what we seem to be finding is that it's more the changes in DST and the other sort of in situ space weather effects that are causing the changes in the spacecraft orbit. So because they're much better correlated with DST, for instance, and KP.
Yes.
So if you look at this diagram that you have here,
yes.
You know, the big change in DST around about day 290,
yes.
you know, there's nothing exciting except a decrease, which should, you know, not affect our orbit significantly in the X-ray flux. Yes, there's a substantial change in KP. And if we looked again at the F10.7 or whatever, we'd find that there really wasn't any significant event in the direct solar radiation.
Yeah, well, that's the F10.7.
So it's quite it's a interesting question as to how much of the orbital changes are associated with changes in the solar radiation versus how much of it's associated with the geomagnetic activity inside the magnetosphere.
Yeah.
So you've got two effects then. You've got the fact that the solar radiation, when CUAVA-1 went up, is different. So the solar max, if the sun was behaving differently.
Yes.
Also, the orbit is different as well. So you've got two things going on.
That's right.
Yes.
And the same is true of Inspire 2, which was back in 2017, which I'm analysing.
So you really got to look at the two effects then to try to make some sense out of it.
But also there's a significant delay in the particle effect, the particle radiation effects, as opposed to the radiation effects, which happen, you know, very quickly.
At the speed of light. Yes.
Exactly. Yeah.
So it's an interesting situation for Tony and I and others to look at, where
potentially students that we happen to get.
Yes, I think we've now involved 4 students, right? Maybe even 5.
6.
Yeah, 6. Yeah.
Busy for a while, I think.
So it's it's proving very interesting, and I think quite profitable is not the right word, but enriching for the students as well, because they're doing projects on this, and thereby it's obviously enriching to Tony and I.
Yeah,
but I will be quiet for a while.
No, that's okay. I'm happy for you to talk. Okay, Wayne, I probably should shut up there because you've probably got other things.
That's okay, Shane. So it's a matter of, does anybody else want to ask us some questions while Tony's still going? I mean, I'm not trying to cut don't worry.
Alan actually has a question in the chat.
Yeah.
Are computers and
So-
other equipment on the ISS failing due to radiation? Yes, they do fail from time to time, but they've got more protection than these little spacecraft have got, and they have people there that can fix the problems. Okay, so
They have more than one too. That's the other.
yes,
On the
and
ISS,
they've got way more than one. There's about 180 laptops.
yeah, they just bring more up, and if something goes wrong with it, let's run another one.
They can bring another one up, but
Yeah,
there's
right.
180 there, and at times they've got to go around and reboot all of them after one of these trips through the South Atlantic anomaly. Yeah. So it's a very busy place, which shouldn't surprise us. Okay, thanks everybody.